So activity 29.1 is going to allow us to start looking at different polar graphs and kind of comparing and contrasting them and moving between forms, rectangular versus polar. So if you look here, these are some examples of some polar graphs. And basically a polar equation is going to be an equation that instead of using our x and y traditional rectangular equation, we're going to use r and theta. Now, we talked a little bit in the previous lesson about making sure that our calculator is in polar mode under the mode menu. And if we investigate the graph of r equals 3, I'm just going to zoom 5 on this one, get a nice zoom square. Notice it looks like we have the equation of a circle. Again, it looks circular, our graph. It looks like it has a radius of 3. It's centered at 0, 0. It essentially looks something like this as we graph, right, all the way through here. Okay. Now, to confirm that, or to show this then is a rectangular equation, going back to our equation of the circle that we talked about previously, our center is at 0, 0, our radius is 3, so r squared is 9. This would be our rectangular formatting. Now, from previous talks, we know that r equals 3. Well, we know r is officially equal to x squared plus y squared. And if we square both sides, these cancel, and we can confirm that we get that equation of the circle we wrote above. Okay, now continuing on with that idea, if we compare these three graphs, notice I have them graphed over here to the right. Notice they are all circles, although they look like they have an oval shape. You have to be careful if you zoom 6 as opposed to a zoom 5. Notice they sometimes just have more of an oval shape than a circular shape, but they are circles, just the way your calculator screen is wider than it is tall. And notice again, all of these have a shift horizontally. They're all circles. And this leading coefficient isn't the radius this time. What the leading coefficient is representing is the diameter. Okay, so we have the diameter here. And these all have symmetry to the x-axis. Well, that all goes back to the format that you see here. The absolute value of A is going to represent the diameter each time. And the fact that these were all A cosines means we are going to have symmetry on the x-axis with a positive A shifting it to the right, a negative A shifting it to the left. So change that so that it's this arrow here represents A is represented going to the left, okay? Now, sine is going to be really, really similar to that, except for when it's a sine graph, it's going to have symmetry to the y-axis, and a positive A will shift it up, negative A is going to shift it down. So as we start looking at these graphs down below here, we have 3 different graphs. And if we start with the central graph, that's just going to be a circle, so r equals a radius of 4. And notice that center at 0, 0 allows us to just put this format, r equals what that radius length is, and rectangularly, x squared plus y squared equals 4 squared. Now this is going to be slightly different as we shift this graph up, as you can see here. Now we need to talk about the coefficient A out front is not the value of the radius, it's the value of our diameter. And because this is being shifted up, it's going to be the value of sine theta. And this time, our equation of the circle, we have a center at 0, positive 4. R squared is still 16. Last but not least, this bottom circle, we shifted it down. So again, we're going to use sine and the negative value of the diameter.